Hello, welcome back to Mini Rust in Rust. This is video 38. Last time we talked about how to make our parser a little bit more complete so that things on the right hand side of a statement that mutates a value could be full expressions instead of just like a single thing. And then at the end we got into the weeds a little bit, and I've figured out a way around that bit, so I'm going to talk about that. But yeah, first of all, let's just say what we're doing generally. What we're doing generally is writing a programming language interpreter for a programming language that looks a lot like Rust. And where we've got to so far, we're writing it in Rust. Where we've got to so far is you can make a very simple program work. We don't have functions yet, which means that we're really, really limited. But we've managed to do enough logic that you can do like a while loop. I basically got just enough code working that my specific example that I was writing can run and give us the right answer. And now we're just filling in a whole load of bits that we skipped on the way there, and we're heading towards stuff that will turn this into a proper language, including adding functions, but including just filling in a load of gaps. But the rabbit hole that we got into last time was, at the end of last time, was how do we remove the strings that we have been storing inside inside these tokens. So every token that we make, a token is what you get when you lex the code, and lexing just means breaking up into chunks of like a number or a string or a name, like a function name or a curly bracket or something like that. Every time we've broken the code up into those tokens, we've stored a string, which is the actual string that led us to say, well, this is a number because it's got the digits 3, 4 in it or something like that. We'll store those digits in here as a string. And we've got this to do here saying, well, we don't need these. And we don't, because everywhere we do this, we also keep hold of a span. So here's where we do it. One example, we keep hold of a span, which is the beginning and end of this token in the original source code. And then the idea is every time we need to get that back again, which is really only for printing error messages and stuff like that, we've got the original source code, so we can just grab the chunk we need out of it directly. We don't need to carry it around with all our stuff. And this is a whole load of extra memory allocations to store all of these strings. We don't need to do it. And I actually got a little way down removing all of these, and I got stuck on how to make a typed syntax tree hold on to a reference to that source code string, which it needed because there are some places where we call toString on this type syntax tree, and it needs to be able to get hold of the actual contents of it in order to turn this thing into a string, exactly for an error message like I was just saying. And I got into a real tangle of how do I make the lifetime of the reference work okay when we're returning an iterator of typed syntax tree. And watch the previous video if you want to get more into that. But what I've realized is the problem is, I'm sure there's some clever way of making those lifetimes work, but it's super complicated. And typed syntax tree, why does typed syntax tree need to carry around a reference to that source code? If we look back at the token doesn't carry around that reference to the source code. It only carries around those numbers for the beginning and the end of where it is in the source code. And then it relies on someone else to actually have that string, which is the source code. And we can do the same thing for typed syntax tree. We don't need typed syntax tree to carry around that reference to the entire source code of the program. Instead, we should be able to figure that out somehow from and use it when we need it. And the reason why we needed to have this string of the token that we're talking about at all is that we implemented display on typed syntax tree. That means we can call toString on it. So let's have a look at some code that uses this. So what we'll do, just to make it really easy for me to find, let's get rid of this implementation of display and see what errors we get. So basically a few places where we are printing errors for the user, or like formatting errors for the user, we call toString on a type syntax tree in order to talk about it to the user. So let's go find where our code doesn't compile anymore. So now that I've got rid of that implementation of display, that means the toString method is not available anymore. Which, by the way, let's just talk about that explicitly. What did I change? The code I commented out was, oops, no, it's off here, right? Yeah. The code I commented out is an implementation of display, and the display trait only has a format method. It doesn't have a toString method, and that's but somehow it made the toString method disappear from this type. So this expression here is a type syntax tree, and it no longer has a toString method. And the reason is the toString trait is automatically implemented if you implement the display trait, and that's the correct way to get the toString method. And the reason is that the default implementation of toString just calls format on that from that display trait. So that's a little bit of Rust weirdness. But if you want a toString method, you implement display. And if you don't implement display, you don't get the toString method. Anyway, point is, here's the place in the code where we need that toString method. So we are in an error situation where the type wasn't what we expected. So what is it? We're saying if when we try and combine the left-hand side with the expression, they somehow don't work. That doesn't combine. This is combining types. This is basically saying if this expression type has a compatible type with this left-hand side, then we're fine. If not, we've got a type mismatch. And when we're formatting the error message, we call toString on that type syntax tree. And in order for that type syntax tree to be able to turn itself into a string, it needs to have access to file contents. So what we were fighting with before was we tried to get expression itself, this type syntax tree, to hold on to an instance of file contents so that we could implement toString. And instead what we should do is pass it in from here. So not use toString, but use some other method that we've defined. What are we going to call it? It's something like format for error, or to error string. Now, because I was always a little bit uncomfortable with using toString anyway, because let's just finish my thought. So it was a little bit weird calling toString anyway, because it doesn't always actually print the full contents of this thing, because this thing could be some very complicated expression. So what my toString method did was actually not really suitable for a toString method, because it doesn't like properly represent the contents of this expression normally. Sometimes it says, like a load of complicated stuff or some summary like that. So actually some custom method is a better way of dealing with this anyway. And given then we have a custom method, we can pass in file contents. And we just don't have the problem that expression needs to hold on to a reference to file contents, because we've got it here whenever we need to use it. So we can completely work around the problem that we had last time. So let's generate this method. And it's actually quite nearby the code that we already had. So let's just put our comment here. And how are we going to do this? Are we going to use a formatter the way we did before? I don't think so. It's so simple what we're doing. We can just do it directly with strings. So we're going to copy most of that code into here. Get rid of the extra bit. And you'll notice there's a lot of to-dos in here because we actually don't know. We haven't yet dealt with the fact that we need to format quite a lot of other types of objects. we've only actually managed to do it for a few things like ints, floats, and symbols, for example. So in this case, self should have a, if I'm right, self will have a span. Yeah, self has a span. So we're okay, right. So, and yeah, so there's a few cases where we need to actually grab the string that actually represents this object, like when it's an integer, a float, or a symbol. So in that case, we're going to say it's going to be file contents. It's going to be a slice of file contents. Let's make a blob of code here. So let, well, what are we going to call them? Beginning and end? Start and end? Let's call them S and E just for a second and see whether we like that in a minute. So first of all, we're going to get hold of the beginning and end of this, the string we're looking for in file contents. Then we're going to take a slice from beginning to end, and then we're going to owned it. Do I need an ampersand? We'll see. I think it's probably okay. So this is equivalent to what we had before. What we had before was saying grab the symbol, like the string that we were carrying around inside ourselves, and just return it essentially. And what we're saying is instead of that, go look inside file contents, which we've now passed in, and get the correct bit of file contents and turn it into a string. That's why we do to-owned on it, because at the moment this file contents bar is a slice of a string. And there's a few other places where we return hard-coded strings, so that's easy. We can just do to-owned on that. Now, why are we doing this? Yeah. So in this situation, so this is when we had an actual number or symbol. So we want to print that actual number or symbol. In this situation, we've got like an operation. So like something plus something. And we basically, instead of like printing the whole expression, which would be too big to fit into an error message, we're just saying it's a float or an integer. And we missed out these other types, which we probably are going to need to do at some point, but they will be similar. And that's it. We haven't done anything for anything more complicated, like if there was a while statement or something like that. I guess in these other cases, we would also want to find the type and print it out in a similar way to this, but we basically haven't thought about it. So this method is really very partially implemented, but it is implemented in the awkward case, which is that. So I think that is the one. Yeah, it was only used in one place, this toString method, and we jumped through a lot of hoops last time trying to make it work by calling toString here, and we didn't initially need to do that at all. Instead, we can pass in file contents directly. So let's just check it works. And it doesn't. We've done something wrong. Okay, so this is one of our tests for the type checking code when it goes wrong. So this is an error test. And it looks like we're trying to slice something starting after it ends. So it looks like I've done something wrong here with either the test or with what we're doing here. So I'm pretty sure this span is the start and then the end, and we're slicing from start to end. Oh no, I know what it is. It isn't start and end, it's start and length. Let's rename these and make ourselves smarter. Because it then becomes obvious what mistake we've made, right? If we name them correctly. Okay, try again. Okay, now it works. Fine. So, all right. So I think we've done the preparatory work we needed to be able to now delete these strings from inside these objects. So let's make a little commit. stop using toString to format typed syntax trees in error messages. That's a little bit too long, isn't it, that commit message? Never mind. Okay, and what we're going to do now is remove the actual strings from the actual things, and we'll see whether we hit any other problems. Hopefully not. And at some point in what follows, I may speed myself up so that you don't have to watch too much tedious code managing. We'll see how it goes, but let's start with me waffling on like usual and see how far we get. So if we delete all of these strings from these objects, now what are we going to do with keyword? I guess keyword is, the keyword is an enum. So these could be all separate. Like it could be a let keyword, a mute keyword, and a while keyword, all broken out in this token kind. But I guess we haven't done that. But we can just get rid of the string part of it. All right. So if I just delete all those things, how many errors do I get? And this is just when we create it. So when we're creating all these things, we need to do it the way they now expect, which is not having this extra string stuck in there. Yeah, so you can see, like, that's where we're doing our memory allocations, by the way. All of this times here, whenever we create a brace close, which we know, by the way, in the case of a brace close, we know it's exactly one character long, and it is a curly bracket, and there's nothing else it could be. Nevertheless, we're taking this this character, which is a closing brace, turning it into a string, which means allocating some memory to put it in, and then storing it inside here. So it is wasteful. So let's stop doing it. Like so. Now, have I gone wrong here? No, but, well, let's see. So, even in this case where we've got an integer, we're still not going to pass it round. So we're going to have to, when we need the actual integer value, we're going to have to go get it out of the source code. But I think that's okay. I think we'll get away with it. We'll see. So lots of places where we're making these things. And we can just delete them all. This is one place where keywords are a little bit different. Okay, now everything in that file, but there's another file which is similar. We've got to do the same kind of thing for that. And again, these are all just very straightforward, just exactly what we were talking about before, just when we're creating them. This is a test code, by the way, that this and there's a whole load of these test functions no longer need to even take in that literal, so we're going to get a load of warnings here on unused parameters, which we should delete from these test functions. So get rid of that too, and we're still trusting we're gonna, whenever we actually need the contents of this string that we're deleting, we can get it from the source code, the total source code of this file. At some point, we may find that we're not tracking that in quite the way we need to, because at the moment we're never really dealing with more than one giant string at a time. when we're parsing, because we haven't actually supported multiple files yet. So when we're supporting multiple files, someone somewhere's going to have to have a reference to the source code of the right file when we're doing this work. But I think we'll get away with that. Okay, so there's a lot of places here where we're creating tokens, and this is going to get slightly less readable in our tests now, because we can no longer easily see when we're reading this back, like which token is which in this list. But I think it's going to be okay. And these examples are all trivial, so it's not a problem anyway. But yeah. Now, what is the Vim foo that I'm after? That's it. Okay. It's DT bracket to delete, and then T means find, but don't include the thing you find. Like find a character, but don't include the character that you find. And then open bracket is the character we're looking for. There's a little bit of Vim foo for you. Did I just do the wrong thing? No, it looks right. Okay. I may have got distracted with my Vim talk. What editor do you like to use, viewer? I've been toying with Helix. It seems really cool. But I'm really addicted to Vim's ability to just autocomplete from nearby symbols, which I always get by pressing Control P. So when I tried Helix, I tried learning all the cool new ways of doing things. It seemed really cool. I couldn't get over the fact that I didn't have that capability. I hear there are other editors which you use the mouse and stuff like that, but that's all Greek to me. Obviously it's not, by the way. I used to use an editor like that, and I painfully taught myself Vim. And I'm so glad I did. It makes the most boring of tasks fun, because oops, that's not right. Anything you do in Vim is fun. Even writing like prose is fun in Vim. DT bracket. You'll notice I'm repeating operations a lot in Vim. That's pressing dot. It's one of the nice things about Vim. When I've done that DT bracket once, I can just press dot to do it again. And then if I do something different, then dot no longer means what it meant, so I have to go back to pressing it, which is why I had to remind myself what it was I was doing. So again, DT bracket, nope. Can't type. There we go. Alright, I'm just trying to find Vim Waffle to get us through this. What have we got left? More. Yeah, so this is all just test code where we're constructing instances of tokens, and we used to pass in the string. We don't need to anymore. What else? Token keyword. Oops! Oh, I've deleted too much here. This should be a keyword let. Like so. What else? All right. So yeah. Oh, this is the other constructor. DA bracket to delete an entire bracketed thing. And these just take in something like that. Lots of keywords and non-keywords. So these are all just things where we're constructing tokens. We didn't even want so we're like matching on tokens. We didn't even want the thing inside the brackets, that string. Here we're constructing them. Yeah, this was a particularly painful place where we had to construct this expression just to check. We had to construct these two tokens, a semicolon and a brace close, which we're just passing in to say these are the things that could be the end of. This would mean that you got to the end of the expression if you hit either a semicolon or a closing brace, and we had to pass in a whole new string into there that felt really wasteful, so we don't have to do that anymore. It's great. I guess the whole thing was wasteful generally, but that felt particularly flagrant. So here we're getting the symbol. Okay, so now we're getting to something interesting, which is we're trying to turn a token into a symbol, a token kind. We're trying to change a token into a token kind. So I think the answer to fixing this is to have these token kinds also not hold, they already don't hold strings. So it's fine. Oh, no. We have, no, the problem is we're making a symbol token out of a token kind. Is that right? Yeah. We're making a symbol token out of a token. We're getting out the token kind. That used to have a string in it. It doesn't anymore. So symbol token can't have a string in it. So that means this symbol token thing here can't have a string in it. It can only have a span in it. Which is fine. That means our new function can't take in that string anymore. And we're going to find out whether, when I said it was fine, we're going to find out whether it's fine when we actually make use of these symbol tokens. We're going to need to, at that point, get hold of the actual name of the symbol at some point, and then we're going to get it from the full source code. So here, so leaf token kinds also should not contain strings. This is going to break more code, which we're going to use compiler-driven development to fix. So, leaf token kinds don't have symbols in them anymore, but it's okay because symbol tokens don't need them anymore. So we're all good. And here's where we're constructing some. And therefore we don't need to pass in these literals to these test functions. This feels very familiar because it's similar to what we were doing with tokens. These are now leaf tokens, which are kind of it's like when we know more about a token than just that it's a token. We know it's specifically a leaf token, which is like a thing which is like at the bottom of the tree of tokens. So it'd be a thing like a number or a symbol or something like that. All right, so just changing all of these, which we weren't using anyway, to not match on something which doesn't have anything inside it anymore. So here we're not getting hold of the literal. So we're going to, this is one situation where we need the source code in order to use the token, the span. Oh, no. This is another situation where, yeah, okay. Now we need to actually do something based on whether this operator is a plus or a less than or equal or whatever. So I think it is, yeah, and we're constructing then the specific type of operator token based on what that string value is. So this thing is not going to have a literal in it. So we'll delete those. And actually, in fact, before we do that, let's just make certain that we're okay with turning this thing. So this is changing from a token into an operator token. And this is a similar example to what we fixed earlier, which is that we're currently using this try from trait, but that means that we got no way of passing in extra arguments here, and we need to pass in an extra argument. So I think what we're going to do is remove this implementation of try from and find out who complains that we ought to be able to do try from on it. Here we are. And instead we're going to call some kind of custom thing called like I guess let's call it try from token, and we're going to pass in the source code, which with any luck we've got here because there's a file contents on stuff. Hooray, we have it. So I guess this is probably, what's the right order of arguments here? Probably the token and then the file contents. So we're going to make a custom function instead of calling try from. And look, again, it's right nearby where we need it to be, so that's great. And it's going to be something similar to this, except this should be called token, I guess. And if the token is an operator, we need to figure out what type of operator it is. Oh, I'm glad this is actually going to work. And we're going to have to figure out the error type, which is not operator token. Yeah, so this is exactly analogous that we used to use the display trait so we could have a toString method. Oh, I've messed up my rename that I did. And now we need a custom thing because we've got to pass in file contents as well as token. So instead of matching on this thing we don't have anymore, we now need to match on. I guess we need to do a little bit more work inside here. Oh no, we're going to let's do ourselves an intermediate fix here where we get hold of the literal here. So first we get hold of the span, which would be token.span. And then we're going to let literal, and this we're going to do this. To do remove this when because it's only needed for operator, is that right? Oh no, hold on. Yeah, no, this is I'm making this harder than it should be. This match is really only ever looking for operator, or so I'm wondering now why I'm not doing an if let instead of a match here. I think I should be doing yeah, I should be doing an if let. So let's change that to while we're here. If let if it's an operator, then do all of this stuff. Otherwise, do this. Don't think I need that. Oh, badly have I messed this up now. Slightly badly. How's that? Okay. Just please compile for a second to show me that I've got my curly brackets right. I'll line them up manually to check it looks sane, and then we'll carry on. Okay, so all that was just faffing around so that I could do this stuff inside here, because the only case we care about is when you have an operator, because the whole point of this function is to turn a general token into an operator token. So remove this when... No, don't remove it. We need it. Okay. So I don't want to call this literal anymore. Well, no, I guess literal is fair enough. So literal is going to be file contents from start to start plus length. It's going to be just a reference because it's just a slice of that string, and we can match on it. And if it's a plus, then this is confusing me. Oh, it's because plus should be. We're still passing in literal. Yeah. I haven't yet changed the thing that means that this needs to take in a literal. So we'll fix that later. Maybe I should. No, we'll do. Okay, and then this is just that the name of this has changed. And why is this complaining? That's because it needs a toString here. So we'll fix this in a second because I'm worried I'm going to do this wrong if I don't. And remove our trailing comma, and we've finally got something that makes sense. Okay, so finally we've written our try from token function. What it does is it looks for things that are of type operator, otherwise it's an error. And then it finds the bit of the source code, this file contents, the right section of the source code to find out which operator it actually is, because it might be a plus or a less than or equals, and future lots of other things as well. And once it's done that, it returns this operator token thing. An operator token thing has an operator token kind, which is currently either a plus or a less than or equals. And that thing in itself holds onto a string. And I'm going to get rid of that right now because I don't like it. And we don't need it anymore. I hope and trust. And this is where we construct one of them. So we can, while we're here, we'll just change that too. So this is again a familiar pattern of our test constructor function, takes it in. We don't need that anymore. So there's only two types so far. I'm glad, you see, at this point, I'm glad that I haven't done a whole load of other operators and then I have to go through the source code and fix it many, many times. So now that we don't need that anymore, we don't need that anymore. It's still okay for us to make literal as a separate operation and then match on it. So we can continue looking for other errors. Here's another example. So in this situation, we need to get hold of the literal in order to actually turn this into a number. So when we found it's an int, we're going to use i32 from struct radix on it to find its actual value because we are in the evaluator now. So we're going to do something very similar. We're going to get hold of the actual literal from the source code, which I hope we can do because self has a file contents. So this leaf thing should have a span, yes. And literal will be self.fileContents, exactly the same as what we had before. So a reference to, this is the way you take a slice of a string from start to start plus length. I'm wondering why I'm storing start and length instead of start and end, given that I'm doing this a lot, but we'll see. So now I've got a literal. So then I don't have the literal from here, but it's okay because I've now made it a different way, so I can still use it in this thing here, which makes an F64 from a string. And here we don't need this ampersand because S is already a str. This should be literal. So it looks like every time we're making one of these things, we need the string literal as a str, so we may as well make it outside instead of extracting it inside each branch of the match like we were before. So this is looking neat. It's looking like it's going to work. Those were the bits that I was a bit nervous about. So now more dumb stuff. These were never used, so there's no worries about removing them. Okay, so this is a situation where we're actually using the symbol again. So this is an assignment statement, and we need to set something in the environment, and we need to know the name of the symbol. So that means we need to get hold of the symbol literal. So I think this is all going to work the same, which is that we get hold of the span of the symbol. And then we get hold of, let's call this symbol literal equals self.fileContents. Now this is where later we may have trouble, because that file contents, at the moment we only have to worry about one thing, one source code file, but when we have more than one, will this instance of an evaluator have the right file contents, or will we need something cleverer to go find that? So this is going to be called symbol literal. Okay, that looks like that's working. And we'll do exactly the same here. This is called symbol literal. I think taking these slices every time we do a piece of work like this is probably okay. Grab that in case I need it somewhere else. This looks like another place where we're setting a value into the environment. And this, I guess we can reuse the same variable here. This is just symbol literal again. Let me double check that. So in this case, we are doing a mutation, and we're getting hold of the old value of that symbol in order to modify it, and then once we've found the correct answer, we're putting the updated value into the same symbol. So this is right. All right, where else do we have that? So again, we don't have a literal here. So this try from, okay, this is an example of a try from that we're going to need to replace with our own try from. In order to make a mutation token from a token. So where does that fall down? Here. So, all right, so check token of type takes in something that is a try from Lexa token. So I think we're going to need our own trait here. Instead of a try from Lexa token, we're going to have to do a try from some kind of trait called try from token, I think. So what is type token? Yeah, I think that's right. So let's go back to the code we commented out, and let's define our own trait. Instead of try from token, we're going to have some kind of trait. So this is getting more complicated than I expected. We're going to call it try from token, and it's going to have it's going to have a type, an error type. It's going to be very much like try from, but it's going to take this extra argument, which is called file contents. And we have to think about, should I have done this for the other example we had as well? Should that also have been implementing this trait? So now we've got this trait. This code that we've commented out is going to get commented back in, but instead of it being an implementation of try from brackets token, it's going to be an implementation of our new trait, which has a similar, confusingly similar name maybe. And it's going to take in a file contents. And the point of this is that the try from trait seemed to fit our use case before, right? Because it was I'll think about that in a second. Because we wanted to convert from one thing to another, And then there's some other code which we'll get to in a second, which says you can pass in anything which implements try from, and I will be able to use it. So that's why we need a trait at all, because that other code needs to be able to say you can pass in anything that implements try from token. We'll get to that in a second. So now that we've got file contents, we can get hold of a string literal. So let's implement that while we're here. So that'll be, let's start length. I mean, it makes me wonder whether holding this span as just a tuple and then having to name these things correctly every single time is making life a little harder than it should be. Maybe the span itself should be some kind of type that makes this easier. It makes it easier to take a slice like we're doing, because we're repeating this code a lot. So this is something maybe I'll put in a little to do here. To do. We are repeating this pattern a lot. Maybe span should be a cleverer type. I mean, in fact, maybe there is a cleverer type already that it could be, which is like a range or something like that. Anyway, so now we've got a literal. We don't need to get the literal out of mutating equals, which doesn't have it anymore. We can just match on this new thing that we've made. What have we done wrong here? Too many brackets. There we go. And plus equals shouldn't take in. So plus equals and times equals shouldn't hold strings either. So we've just got this tower of compile errors that we're building and then hopefully removing. Oh, I thought I was going to sneeze, but then I didn't. Okay, so what does it say? So it doesn't like this. Yeah, self should be sized. Or maybe this should be, I think maybe this should, if we do that, is that better? Something can only be try from token if it's already sized. I think that will mean that that error message goes away. Yeah, so you can't return type of a thing of type self unless self is sized. All right, so what else? Follow the rabbit hole of errors, including we've stopped supporting this. I'll stop needing to pass in these literals to every place where we, in our test, where we construct these things, these leaf tokens. There we go. More of that. Okay, loads more test codes. We can just simply delete. Simple token doesn't contain that anymore. More of this. And just lots more. So this is all just operator tokens no longer contain these strings, so we don't need to pass them in when we construct them for our test. And as I say, this is the kind of situation where it was maybe a little bit easier to read the tests before, because you could see which one is which just from those strings that we're passing in. But we lose a tiny bit of readability in our tests. But the tests are now representing reality correctly, right? It's a leaf token which doesn't actually contain those letters 3, 3, but it does refer to them. What would be nice would be if in our tests we could somehow assert, instead of having to figure out this span, we could just assert that the span correctly comes out as AA. So that might be something that we could fix later. In fact, let's add a little to do for that. Here as good a place as any. To do. Instead of opaque span values, can we assert that the spans match the strings we expect? Okay, continuing on. That doesn't contain a symbol token anymore. But it doesn't help my typing that I have to look around my microphone whenever I get to a bit of the keyboard I can't find with my fingers, which is almost all the bits of the keyboard. Alright, how are we doing? I thought this was going to be a really short little video where we just did the first thing that we did. And I thought, no, let's go for it. Let's do all of it. And of course, it's a huge rabbit hole. But I don't know, it's all good content, isn't it? Or it's all content. Okay. Maybe we'll do a bit of fast forwarding here if this goes on too long. Well, that's the end of those things, so it's not been that long. No, there's a few more. Right, now to more interesting errors maybe, or just the same errors in other things. All right, so again, when we're dealing with these mutation token kind things, they no longer have strings embedded in them, which we're ignoring here. Now, check token of, okay, so here's the situation. Check token of type was implemented, took us ages to figure this out, but it's implemented on every type T, or it can return a result of type T for anything that implements try from brackets token. And instead, I'm saying what we should do is only if it implements our new special trait, which we call try from token. And we'll have to do that here as well because this calls that. Oops. And we've managed to make at least one of the types that we did this with implement try from token. I suspect there's at least one other or we wouldn't have bothered with this whole thing. But what check token of type does is it calls try from. Now it's going to call try from token and then does its work. And it takes in an extra argument. So we have to pass in the file contents. So this is where we get file contents passed in. So it's all making sense so far. This self thing, which is a parser, I guess, yeah, or parse, has that file contents. So this is what I was worried about. At some point we get to a place where we're calling one of these methods that requires file contents and it doesn't have access to it. But so far, all the places where I thought that was going to be tricky do have access to file contents, so we're okay. Okay, so check token of type. So we're saying that mutation token doesn't implement try from token. So let's look for where we implement try from. Yeah, here we are. So these things implement try from brackets token, and we're changing them to just implement my new trait, which is called try from token, which is very confusing. And it should take in the file contents, like so, which is not used. That's interesting, isn't it? That's really interesting. So why not? When it's a symbol, Okay, so when it's a symbol, it doesn't actually matter at this point when we're converting from a token into a symbol token. It doesn't matter what the symbol is. It will just pass in the span so we can find it later. That makes sense. Okay. So check token of type on token. What's the error? Leaf token doesn't implement try from token. Okay, so we're not yet dealing with try from on a symbol token which implements leaf token, which returns leaf token, but somewhere we've got impl try from on leaf token. Yeah, okay, so that's the one. So instead of implementing that general trait, we're implementing this one. And again, we're not actually using file contents here because these things are all just an int. It becomes an int type, and you pass on the span so you can get hold of the thing later. But yeah, so basically our generic type of converting a token into some other thing like a leaf token sometimes cares about file contents, and at the moment it's only the operator type that cares about which operator it is, because when it's an int or a symbol, it's good enough to know what type it is. We don't have to know the details. So I think that's all making sense. Now what else? When we're trying to turn a symbol token into a type constraint, we're getting hold of this symbol. Okay, so this is another situation where we've currently got this generic method called try from, and we're going to, instead of implementing try from a reference to symbol token here, we're going to need to do something specific. So I guess we'll just comment this out and follow the compiler again. And here we are. So this is where we call it, and I'm just going to say, instead of saying try from generically, we're going to say try from symbol. I guess symbol token would be the kind of simplest thing to say. We're going to generate that function, go to its definition, and we should hopefully be nearby the thing we just commented out. So let's just extract the whole of this, move it near to where we create our new function. And the bits that we need are, it's going to return, it's going to return a result of self, met error. Like so. And it's going to take in not just a symbol token, which we'll call symbol token, but also the file contents, which hopefully is going to be easy enough to get hold of. Keep that to do because I haven't read and understood it yet. Get rid of the rest of this machinery. And now we've got file contents. We can say the same, this pattern again, which really feels like that to-do we wrote earlier needs doing, doesn't it? Symbol token. Oh, whoops. Don't know what that was. Symbol token dot span. And then let's keep this thing called symbol. This is going to be file contents. It's going to be take a slice of file contents from start to start plus length. So again, we're using the actual what's in the symbol to decide what the type is, because this is what we're doing. We're converting from a symbol token to some kind of typey type thing, a type constraint. Okay, and then when we call that, I'll fix these in a second. yeah, here we need to pass in file contents, which I hope we've got in self. Yep. So that's all fine. Right? No. Oh no. No, we haven't got a self here, we just got file contents. So we're okay. And declared type doesn't have a symbol, so we're going to need to get hold of, yeah, again, we've got file contents here, so we can get hold of. So again, we're going to do the same thing again. Get hold of our span on our declared type. And then let declared, let's just call that decal literal file contents sliced from start to start plus length. Now, hopefully we've got tests for all of these cases. We should have, if we've done our test-driven development right. There should already be a test for each of these. And then we can just turn that into an own string. And everything is fine. Right, good. So it looks like try from symbol type is going to work similar to the way we've done other stuff. Now, just some dumb stuff. Doesn't have a symbol inside it. And this should be try from symbol token. I think these are just tests. Oh, and we need to pass in. Okay, we need to. We're testing this try from symbol token function, and it needs a file contents passed in now. And in order to match the error messages that we were seeing, we need to say the span from 0 to 3, or 0 from 0 of length 3 should be to get whatever gets stuck into, whatever gets understood as an F64. So that should be okay. And these things no longer have string literals inside them, which is good because we were repeating ourselves here, so that looked a bit wrong, didn't it? Did I just delete something I shouldn't have? No, that's right. Like so. Like so. And a few more. No. Yes. When I'm doing this kind of task, I generally have absolutely no idea whether I'm like nearly there or whether I've got another 10,000 errors to fix. I'm kind of just letting the compiler completely guide me. To me, sometimes programming is just finding ways of switching off my brain and letting something else do the thinking for me, which I think it has some advantages. Like there's sometimes some certain types of test-driven development that's a good thing, to like force yourself to think through the tests. But sometimes it's just a really bad thing. It's just that my poor old brain is not very good at thinking. Wow, have we got rid of all the errors? So we run our tests, having made all these changes. They all pass. Therefore, we've done it, right? I didn't put any hacks in. Let's just check our diff as we go through. But yeah, so here, this was all perfectly sensible. And when we're evaluating, yeah, there's a lot of stuff where we don't even need the literal, but then here, this is an example of where we do need the literal, but we have access to file contents. So lots of places where we just no longer need those strings. So we've really reduced the memory usage, or number of memory allocations especially, of our program by a lot. And lots of test code. Test code. Test code. Yep, don't need to pass it in when we're constructing. And then getting quicker as we scan through because we're more confident. Here's where we did the... Oh yeah, the last thing I wanted to do was I created that trait, try from token, in just a random place. And I would like now to think about where in the source code does it live. But let's just continue. Yeah, okay, so the diff looks fine. Let's just find try from token. Trait. I don't remember what file it was in. Okay. And we implemented it we declared it just in the middle randomly before it's first time we used it. But I think we want this to go somewhere near the top. Yeah, because there's another implementation of it above where we declared it, which feels totally wrong to me. So let us declare it after our implementation of parse, maybe. Oh, that's long. I think that's right. If we put it after this, and after the iterator here. And I guess we should have some kind of dot comment for it. Convert from a token into some more specific type. Essentially, this is like types that implement this can be used in, I think it was, where was this used? Token of type and check token of type. Token of type and check token of type. What are those? They are methods on parse. So I guess we should do it properly. Like so, and then we'll get nice links in our documentation. I missed the tick. And the only way I can check those work is by actually following those links, which they do. Good, right. So I think that's enough explanation. All right, let's just check our tests run. They do. All right, so we're finally there. We have removed string literals, well, strings from token types. Instead, well, let's make a longer commit message. Instead, just hold spans, which allows us to look up the full literal inside the file contents when we need to. All right. I hope that was enjoyable. That was like very much not about programming languages and more about just refactoring the particularities of this Lexa parser evaluator that we're writing. But it's all part of our mission to make these tokens a lot more sensible. So now the kind of a token is just int, float, or operator, and we're not holding that string inside. So we're doing a lot less memory allocation. We made ourselves a couple of to-dos. So next time we might figure out some of those to-dos, especially that span thing is really annoying me, that we wrote the same code loads of times. We've also got other to-dos we can go through just to make our code a bit nicer. And then at some point we'll get onto the more interesting bits, like making our type checker actually check more stuff, filling in all the different types of operator, all the different types of number, stuff like that, implementing functions. So not sure what's coming next. And if you have thoughts about what the best thing to do next is, or the thing that's really jarring with you that's not currently done or is wrong at the moment, hit me up on Mastodon. One other thing I was going to do while I've got you is I was going to recommend you some more of my videos. So if you've got into this because you've been watching these videos where we're kind of live coding Rust, I'd just like to recommend to you, by the way, I have a YouTube channel. If you're watching this on YouTube, feel free to continue watching on YouTube. If you want to jump to this PeerTube server, infosec.exchange, which very kindly hosts my videos, then there'll be less like tracking by big tech, but otherwise it's just the same basically. But what I want to encourage you to do is to explore a little bit further into my videos, because if you go back past all the mini Rust stuff, there's a series before called Rust 101, which just is like teaching Rust from the beginning, probably not for non-programmers, but for people who know some programming. And there's some good stuff in there about async and things, which I think explains stuff reasonably well. If you go back before that, there's all kinds of other lectures and fun stuff about maths, stuff about matrix, lots of videos of me writing Snake in different programming languages, like some more Rust stuff about React, about why I don't like dependency injection frameworks, how Kotlin's nice, Silly One, stuff about async Python, stuff about something that I would recommend for a lot of people. If you haven't got your head around Unicode, have a look at the interesting characters video. There's Elm, there's Godot, the game programming environment, some stuff about Rabbit Escape, which is a game I wrote, things about how to write a programming language, which are probably relevant to people watching this, but maybe a bit basic for you now. More stuff about Elm, things about Git, more Snake games, some very beginner programming stuff like how to make a snowflake Christmas card in either Scratch or in JavaScript. What else? Android coding, mocking frameworks, template, C++ coding, esoteric things, REST APIs, Vim, more Git stuff, coding a simple game in Python. This is my Raspberry Pi game. The ones that are probably most popular on the internet are the ones about Scheme, which is a Lisp programming language. People like this stuff, so if you're interested in like functional programming, might be worth having a look at these Scheme videos and some on JavaScript. And if that's all a bit confusing, they're arranged into playlists. There's also playlists on YouTube as well. So yeah, you can just scroll through the playlist and find the general topics, including the Scheme series here. Also on my infosec.exchange or video.infosec.exchange area, there are some videos by on category theory, which I didn't create, but I thought they were awesome, so I've uploaded them. And also there's some videos from the MIT programming course about Scheme, so you can find those not here. In one of my, and they're different channels here. So there's the category theory and the structure and interpretation of computer programs lectures channel, which has some awesome MIT videos about coding in Scheme, or like what programming really is, or something like that. So check out video.infosec.exchange/a/Andy Balaam, or follow me on Mastodon. I'm at Andy Balaam at mastodon.social. If you're interested in other videos other than mini Rust in Rust. Hope you've been enjoying the series, and see you soon.